so thank the organizers for inviting me. Previous time I spoke at your series of conferences 4 years ago, and so okay. So what happened? What happened during these during this 4 years? So once more, please inform me if you don't see my screen and my cursor. Do you see it?
Yes, I do.
Yeah.
Okay.
We see it. Yeah.
So the main change during these 4 years, that first we have much better observations. I shall mainly use the final results of the Planck observations. It was issued 2 years ago. Recently, a new experiment was made at the Gamma Cosmology Telescope, but still it appears only a month ago, so we still are thinking about it. So once more, I shall speak only about the Planck. And so really the statement is that it will be the main statement from what follows from observational cosmology that can be also used for particle physics. The statement is that the all existing data about the very early state of the universe can be described using, in the simplest case, only one parametric inflationary models. So they use only one constant, which status is, I would say, the same as the fine structure. It was as the state use of a fine structure constant. It is not derived from any more fundamental theories taken only from experiments. In our case, from observations. But of course, we are prepared for future observations, which may discover new constant, and so of course we have much more complicated model. But once more, at the present time, I shall show you one parametric model, which in fact produce practically the same prediction, formally the same. I shall explain in which sense. Okay, and so this is from observation. From the theory, we speak about small corrections to these models. In particular, I shall speak about quantum correction. And from the absence of this correction, actually, it is expected to be really that this general hypothesis would work. So, okay, and still once more, in one point, I shall say you about possible discoveries, expected and not expected. And so in particular, is to show you that we are really prepared to some unusual things. I shall speak about this possibility, additional possibility to generate large peaks. And finally, the third thing which about the thinking, we now understand that inflation as always it is unstable state. It's metastable, but it's an unstable state. No quantum system may live in an unstable state an infinite period of time. So something was before. At this moment, we don't have any observational data which would permit us to give a choice between different theoretical possibilities. But still, I shall list some. So something was still before inflation. And this is a very compressed picture of what we know in the standard, I would say, in the standard model, cosmological model about the history of our universe. And this behavior, it's just this curve more or less presents the behavior of a scale factor. And you see that it is convex here and it is convex here. So during inflation and during the present state. And this means that at least the first stage and the fourth stage, the expansion of the universe is accelerated, and just the opposite, it is concave here at the hot Big Bang. So hot radiation dominated stage and hot method and cold, excuse me, and method dominated stage. And so in this second and third stage, the expansion of the universe was decelerated. Okay, so I shall mainly speak about inflation, but I say in a few words what might be before inflation. Okay, so inflation, once more, I shall speak about inflation in a narrow sense, in the sense of viable inflationary model, because sometimes it is used in a very broad sense, and this results in critics. So in the minimal variant of the inflationary scenario, once more, of the viable models is based on actually not on one hypothesis, but on two independent hypotheses, or you may call them ideas. So, and once more, I emphasize the independent, and I shall explain in a minute why. So the first hypothesis is a hypothesis about the behavioral background. It's just the hypothesis of the very existence of inflation, or better to more exactly, more rigorously saying quasi-de-Sitter stage, a stage of accelerated close to exponential expansion of our universe in the past, which preceded the hot Big Bang with decelerated polar expansion. And the second assumption is what is the origin of all inhomogeneities, because we are not interested only in the exactly homogeneous and asymptotic universe, where almost all interesting effects are connected with inhomogeneities. So what's the hypothesis about the origin of all inhomogeneities? It is the hypothesis that produced just from this effect, gravitational correlation of pairs of particles and antiparticles, and field fluctuations in the course of inflation. So in the course of the stage which was assumed in the first hypothesis, from which initial state? From which initial state we cannot define that for all modes, so it is not an absolute vacuum. So, but what we can introduce is adiabatic vacuum, adiabatic no particle state for some range of Fourier modes, of spatial Fourier modes, not for arbitrary long modes, long wavelengths, for, as I said, for finite range of scales, but it covers all observable scales and actually and much beyond them. Okay, so the second effect, notice, very short notice, it's actually of the same type as particle question, but in black holes. But fortunately, in our case, we don't have any problems with loss of information, firewalls, transporting energy, and so on. Actually, even making more compression, both assumptions can be combined into one. I just follow the way of presentation, which was actually in my paper in 1979. It's an assumption that some part of the world, speaking, so it may contain many universes, which includes all its presently observable part, was as much symmetric as possible during some period in the past. And when formulated in this form, you will really have an explanation of the error of time in our world. It is non-universal exponential because it is due to specific initial condition, but okay, it's work. So once more, this hypothesis, as compared to other alternative mode, I would say that for me, once more, of course, these are two hypotheses which have to be compared with observation data. It's where I should emphasize that where have analogies in the existing physics, so they are not completely opposite to what we see now. So the first hypothesis is actually based, though it was not initially, but now it can be presented in this way. It's also that substance which produces initial inflationary stage by its properties from the not quantitative but equalitative point of view is very similar to interpreting dark energy. And so inflationary hypothesis may be formulated just in the form that we have something similar, that we have some primordial dark energy which qualitative properties were very similar to properties of the present dark energy. The only point, of course, I should honestly say that we assume much higher degree of of metastability when we actually see that it existed for about 60 e-folds at least. For present dark energy, it was more or less similar to the cosmological constant, I would say, at least for 3 e-folds. And the second effect is it's very just constructed in complete analogy to the effect of creation of electrons and positrons in an external electric field, which I would say almost confirmed by experiment, not exactly. Okay. So what we have from this hypothesis, we have a prediction for something which we see here, and where really the most. Once more, I shall it will be written a little bit be low, but I shall emphasize once more, we assume that up to energies of inflation, the main properties of the present physics, namely Lorentz invariance and the absence of additional spatial dimensions still remain. Of course, once more, it's a hypothesis, but at present, my statement is at present we don't have any necessity to assume that Lorentz invariance was broken at least energies. I show you exactly at which energies and additional spatial the dimensions if they exist, they still gonna show themselves. And what we have to obtain from any concrete model. So the general property of all inflationary models that we are predictable. We choose these initial conditions. Once more, it's not the absolutely all initial conditions, but for sufficient amount of initial conditions, we have models, we have equations, and so we can make all predictions what we see now. Okay, and the most important other prediction about this perturbations which we actually see now from the fluctuations, anisotropy, and polarization of the cosmic microwave background. In particular, we can determine the structure, for the structure. So you see, I write this in this way. So isotropic spatial curvature is, if it exists, is included into the monopole component of this perturbations. So that's why I can expand all spatial inhomogeneities into three-dimensional Fourier harmonics, and then we have power spectrum. So it's a square of the amplitude in the Fourier component, and we are interested in this quantity. We are interested in this slope defined in this way. By -1, it's only for historical reasons. Actually, it was introduced initially by for some other quantities which will lead to -1. In this reiteration, it was introduced in one of the early papers by Jim Peebles, who has just got Nobel Prize for his contribution in cosmology. And also the generic prediction, it will be that this perturbation, they have trace component, which is scalar perturbation, and they have priceless and transverse component, and this is simply a normalization condition. And we're also interested in the prediction of this quantity. And non-trivial prediction of all viable inflationary models, because there exist many models which have been already studied by observation, but this quantity is small and at the least of the order of this. So this quantity is small. This is the prediction of also, and this quantity is also small and no larger than first order in this small quantity, but actually it can be much smaller. It's another question in which I shall only mention, but I don't have time to speak it in more detail. Of course, this quantum effect is my second assumption is the quantum gravitational effect. So of course, native perturbations are quantum even at present time, but it appears that after emitting a very small part of them, they become effectively classical but stochastic. So essentially, the prediction about the present space-time metric, that it is stochastic, and in the first approximation, it's Gaussian, and this is confirmed. But I just want to emphasize that all predictions are beyond semi-classical gravity. By semi-classical gravity, we mean the very approximate figure in which we have quantum matter, and classical gravity, and the classical matter is driven by the average value of the quantum energy momentum tensor. So no, they are all beyond this approximation, because in particular the prediction for the average value of all perturbations is 0. But the fact that the average value is 0 does not mean that the perturbations are absent. So it is, once more, it's a Gaussian quantity with 0 average value and non-zero dispersion. And this is the actual picture of the anisotropy. Anisotropy, of course, make my background, and typical depth of these oceans and typical height of this mountain ranges are of the order, relative order 10 in power minus 5, so about 30 microkelvin. And you see, as I said, we have this. That's why we mostly use this spectral expansion into multiples, and this is how this one parametric models, which I shall show you in a minute, just how well they actually fit with very, very complicated curve. And this is in case of temperature anisotropy. Then on the level of 10 in minus power 6, so a few microkelvins, there appears only linear polarization. And this is the picture. You see how well it is also fitted with polarization. And non-trivial, also another non-trivial prediction is this polarization, like the traceless tensor on the sky, can be decomposed into a so-called E mode and B mode. And the non-trivial prediction is that the module B mode is absent. It indeed also is confirmed, and the prediction we expect, but we expect this B mode on the level below 10 in minus power minus 7. So we are now speaking about the expect that less than 1 microkelvin. Okay, so you see in general how good is the prediction. So apart from possible deviations from here, that's a possible 10% effect, which is still not confirmed if it is really primordial, is for future. I shall mention it in possible future discoveries. But speaking about now translating this graphic information into numbers, I would say what we obtained from this experiment, from this is the final general announcement of a Planck experiment, we obtained two new numbers, two new dimensional numbers: the amplitude of the spectrum, and this is square of the square of inhomogeneities of the universe. So it's a kind of generalized cosmic Newtonian potential divided by c squared, the velocity of light squared, all squared. So okay, so this shows you. So what's more, in all models, and not only in stationary models, actually in alternative models too, we have to take this number only from observations. So once more, at present, the status of a small number is the same as the status of fine structure constant. But also what is measured, the spectrum, this quantity is small. As I said, it is a generic prediction of all inflationary model, but it's not simply small. We actually know its number. In S minus 1. Well, once more, it's not exactly constant. It's actually the prediction is a slowly changing function of a scale. Its average value of a range of scales in which it was measured, approximately from 1 megaparsecs to 10 to the power 4 megaparsecs. Okay, but once more, we are interested now in this number, and this is from the theoretical point of view. For me, it's the most remarkable achievement of a Planck experience, that we really know this number with okay, with good accuracy. As for the gravitational wave, we don't discover the primordial gravitational wave, and this is expected, and this is where it present upper limit, which in particular includes all, I will say now, naive scalar field models, in particular m² phi squared models. That model predicted the value of R at more than 2 times more, so it is certainly excluded. Okay, and so as I said, the fact that this quantity is simply small is the property of all viable inflationary models. But the fact that it is not simply small, but close to some another number, and I shall show you here. It's just gives us a possibility to choose a very narrow class of possible inflationary models. And the statement is that in any inflationary model, why this number should be taken only from observation, this can be predicted, and it was actually predicted more than 20 years before it was actually measured, and predicted in terms of which quantity. When we say that we are predicting some fundamental quantity, immediate question, in which terms? The answer is, and I would say it's a very non-trivial result, this refers to the properties of the inhomogeneities in the universe long time ago. It is predicted in terms of this quantity, which simply characterizes, in fact, how large is the present universe, because actually what happens here, what appears here is the Boltzmann constant, the present cosmic microwave background temperature T gamma, and H naught, Planck constant, H naught is the present Hubble constant. So okay, so once more, this concept shows how, in fact, it's characterized how large is the present universe. Of course, it's not a constant at all. It slowly changes with time as logarithm t, and this means that also this constant is not exactly constant. It's a slowly changing function of k. And up to small corrections, I shall show them later, up to 10% corrections, that's the prediction for this narrow class of models, which you can check by your own eyes without using a complicated computer program, is that modulus this quantity multiplied by this quantity is approximately 2. And really, to show you that this number 2 is which accuracy is needed, I would say that completely different variants of inflationary models will be viable if this constant will be over 1 or approximately 3. So the fact that it is just 2 and not 1 and not 3, really, it's very important. And so once more, just because I'm speaking about, and I'm addressing now in particular students or specialists in the field, just because we may see in literature many, I would say, general and not very specific critics of inflation. That's why I would like to give you answers to these critics, and just because this critics is not, I would say, it's not very scientific, it's in popular terms. So my answers would be also only available. So one statement which you may find in the literature: inflation is not falsifiable and cannot predict anything. Reply: wrong statement. Any concrete, just the same situation is that with any models of any extensions or any extension of the standard model of elementary particle physics. Any concrete inflationary model is falsifiable. Much more. Most of the proposed models that have been already falsified, including the original 1981 model by Arthur Goff. But fortunately, still some models exist which are still viable, including my pioneer 1980 model. Okay, about the predictive power, of course, the less is the number of parameters to be fixed by observations of remaining viable models were larger is their predictive power. And once more, the present state of that, the most predictive models have only one free parameter. Okay, the second critic is the beginning of isotropic and homogeneous inflation requires extreme fine-tuning of pre-inflationary conditions. Reply, wrong. Intermediate inflation attractor is generic and inhomogeneous. It is approaches quasi-deceptive state only inside the Hubble it reduces. And the simple answer that I would say inflation in that model, which I shall show you, is as generic as black holes in general relativity. So this does not mean, you know, of course, that black holes exist and we really discover them, but this doesn't mean that black holes are omnipresent. But still, it simply means that they exist somewhere, so you can find them. Okay, and final remark once more. It refers to the so-called eternal inflation of the fact that inflation model generally predicts many the so-called multiverse picture. Eternal inflation leads to multiverse in which no quantitative prediction can be made. Reply, it's not relevant if not wrong at all, because irrespective of some problems with making prediction in this case, which are used to unjustified manipulations with conditional probabilities. Eternal inflation still occurs outside our past and light and future light quantities. So it's an unfinished process which happens somewhere, I would say, in our space and our time. So it does not affect what we see in our universe up to first up to small terms which are first exponentially small, and second, which was omitted in all previous quantitative considerations of eternal inflation, beginning actually from my 1986 paper. Okay, and so this simplest models produce this observed scalar slope. As I said, first is my original, a little bit simplified R plus R squared models, where R is the richest scalar. So it's modified. It's not Einstein gravity. It's modified gravity because this is Einstein gravity and this is modified. And we can use the first observational constant from which I measured to fix unambiguously this constant. So in this model, this appears that appears new characteristic mass scale, energy scale of this order, and it's really an interesting scale because it's significantly less than unification scale. It produces the correct value of ns minus 1. You may compare. I wrote 35 here, so it's 26, and it has a definite, I would say, target prediction for the future possible discovery. And also, what is important is the first time that we really see that there was real, something very close to the singularity in the past of our universe. The statement is that there was, we see now the traces of a period where the curvature, the Hubble parameter was as high as this quantity. The same prediction follows also from the non-minimally coupled scalar field model with this asymptotically like Higgs-like potential and with strong non-minimal couplings. That's important.
Dear Professor, I'm very, very sorry to interrupt you. I just want to say to you, yes. Only 5 minutes left. Yeah, please take it.
Okay. So I shall very shortly say you. Okay, and so the statement is that this model produces the same prediction. So okay, so I shall actually interested people can see from the whole my slide what other, but what I want to say to you. Okay, I shall show you why these two models, completely different models, produce the same result. It follows from the following fact that in this model, in this non-minimally coupled scalar field models with asymptotically Higgs-like potential, if psi is negative, is very large, then in the first approximation, only during inflation, you may omit this term. And when this appears that can be called geometrization of a scalar, that the scalar phi is locked to the Ricci curvature. And so if you introduce, generically, it's not possible to introduce solutions into the action, but here during inflation it's possible. So if you do here, this model take this lock into account, this model just transforms into my R plus R squared model. So these two models, the Higgs inflation many models and R plus R squared model, and this is the reason why they produce the same results. Okay, but this lock suddenly breaks just after the end of inflation, and the real reason why it's called, because during inflation R is positive, but after inflation R becomes negative, and so this condition it cannot be satisfied. Okay, I think I shall stop here because you and let me only I think I still 2 or 3 minutes, and let me remind you so once more. Okay, still let me show you about because expected discoveries. So expected discoveries, as I said. Okay, sorry, let me only show you. No, it's not here. I skip it. Okay. So most, I think, from the fundamental point of view, most important expected discovery is primordial gravitational waves from inflation, and we have, I would say, a target prediction. So of course it may be falsified, but we have definite prediction in this minimal one parametric mode that it was this quantity, and I think it's very good, because in many other problems, in particular, we don't have any target prediction for the breaking of the supersymmetry scale. Okay, and when a more precise determination of ns-1, it gives us information about the duration of inflation and information about the properties of physics at this energies, and two features which are not contained in one dimensional, which in one parametric models, is local non-smooth features in the power spectrum and local enhancement at the power spectrum of small scale. So it's possible to do. Once more, we don't have a present observational data, but if it appears, it will be proved that some of the black holes which we see now from gravitational wave antennas, if they are immortal, then in fact we are prepared, and we have several variants how to add more parameters to our inflation models, in particular, and this is the topic of my recent paper. So it's possible, but once more, it's not the expected prediction in the minimal one parametric model. And let me only finish with my conclusion. So we have confirmation of typical inflationary predictions that ns-1 is small, and overall always quantity. Once more, it's the quantity which simply defines how large is the present universe, and the R does not exceed this quantity are confirmed. And then the interesting predictions for the elementary particle physics, that we have this characteristic mass scale 10 to 15 GeV. Once more, it follows only from observations, from the fact, from how small are actually the present inhomogeneities of our universe. In the F over R gravity, we have definite prediction for this quantity. So it's, as I said, it represents a dynamical attractor. So in inflation, it's sufficiently generic. Then really, I don't have time. I only announce that I can consider different quantum corrections are considered, including running of constant are considered, and we don't see this effect. And this is expected. And finally, speaking about what may happen before inflation, there are several possibilities, including bounds, but one generic possibility is that before inflation there was something more inhomogeneous and something more anisotropic, a kind of space-like curvature. Singulariety. Thank you.
Yeah, thank you very much. Okay, so I don't see any questions in chat. So
Can I have a question? Sorry.
Okay.
Okay.
Can I ask?
Yes. Yes.
As I understand, during inflation, you have a huge velocity of inflation of expansion, much larger than speed of light. Yes, but we know that space is not empty. There are a lot of particle fluctuation of particles. Maybe there is contradiction between this because this fluctuation will have a huge velocity, much larger than speed of velocity of speed. What do you think about this?
First, I did not quite understand one of the statements in your question. No, I would say no. There is no all velocities properly measured are much less than are less than velocity of light. So once more, I remind you that one of the fundamental assumption was that the Lorentz invariance is not broken at the energies, just as I said, 5 magnitudes of order less than the Planck scale, and actually even up to 10 in power 14 g.
So expansion velocity is lower than velocity of light. Yes.
Once more, actually, if you are speaking about these perturbations, they actually do not in the so-called super Hubble region. They actually do not depend on time at all. So, in some sense, you may consider them as aesthetic.
Okay, so we should finish soon. I just got one question in the chat. Maybe it will be the last question. So the question is, what observables from galaxy surveys could be relevant to constraint inflation theories?
Okay, it is just from galaxies where obtain either speaking about our space, coordinate space. It's the relation functions or the power spectrum. So from the galaxy surveys we obtain, but the same information as we obtain from the cosmic microwave background, only for a smaller scales. So speaking now of scales, say from 100 megaparsecs up to scales of even kiloparsecs, speaking about galaxy size. So essentially the same. So first, as I said, either calculation functions or it is Fourier transform power spectrum, or more complicated construction, the so-called B spectrum, T spectrum, and so on, which also gives us the possibility to check not only the spectrum of perturbation, but is statistic too. As I said, the statistic, the essential prediction actually following from the assumption that initial states for any Fourier mode was adiabatic vacuum. It follows that in the first approximation it's Gaussian, and up to only due to non-linearity of gravitational interaction. So there it contains some small corrections of the square of this quantity. So inhomogeneities are also of the order of 10 in power minus 5. So of the order of 10 in minus 10, 10 in power minus 10. We expect some deviations from non-Gaussianity, and it is this effect which is just now searching from galaxy surveys. The present accuracy what is achieved is about 10 power minus 9. So still we need to extend it somehow one order of negative more.
Okay, okay, dear Alexei, so thank you very much for your very impressive report. And gentlemen and ladies and gentlemen, we have to move further.